Hello, and welcome to Linear Algebra. This is lecture 29. Today's topic is isometries. So last time, we talked about normed spaces. So these are vector spaces where we have a notion of length of a vector, even if we might not have a notion of the inner product between two vectors. So we have a length of a vector and it satisfies four properties. It is non-negative, it's definite, so the norm of vector is zero if and only if that vector is zero. It's positive homogeneous, so you can pull out scalars by their modulus. And it satisfies the triangle inequality. This time, we wanted to talk about linear maps that preserve norms. Right, so this is a common theme throughout the semester. Anytime we introduce a new type of vector space, then we immediately want to understand what are the linear maps between vector spaces that preserve all of this structure. Okay, so just for drawing a parallel, let me recall that two vector spaces, V and W over field F, are the same, in quotes, if there is an invertible linear map T from one to the other. We call T an isomorphism and say that V and W are isomorphic Okay, so now here's definition. If V and W are vector spaces with norms, we say that they are isometric if there is an isomorphism T from V to W such that the size of T of V is equal to the size of V for every V in V. Right, so of course this size is measured in W, this size is measured in V, and we're asking that they coincide. We call such a map an isometry. Okay. So just like isomorphic vector spaces are vector spaces that are really the same vector space, possibly one is in disguise. Same thing with isometries, you have the same normed space, possibly one looks a little different than the other. So here is an example. If you look at 2x2 matrices with complex coefficients, and if you look at vectors, column vectors of length 4 with complex coordinates, these, as we've noted before, are isomorphic. For example, you could use a map T that takes the matrix A, B, C, D and turns it into a long column vector A, B, C, D. So if we measure the length of vectors in M2 of C with the Frobenius norm and the length of vectors in C4 with the standard norm, then this map T is also an isometry. Since the Frobenius norm of the matrix ABCD is equal to the square root of modulus A squared plus modulus B squared plus modulus C squared plus modulus D squared. And that's equal to the standard norm of the column vector A, B, C, D. Okay, so this map, this identification of these two vector spaces also identifies the lengths, as long as this is the length you're using on matrices and this is the length you're using on column vectors. Okay, here's an obvious thing to notice about isometries. So any map satisfying that the length of T of V is equal to the length of V for every vector V in capital V is injective. Since if you have a vector in the kernel of T, then the norm of T of V is equal to 0, but by assumption that's the same as the norm of V. So V itself is equal to 0. Okay, so any map that preserves lengths has to be injective. Okay, so here is a simple theorem. If V and W are inner product spaces, and T map between them is an isomorphism, then T is an isometry if and only if the inner product of T of V1 with T of V2 is equal to the inner product of V1 with V2 for all V1, V2, V. Okay, so you may have been asking yourself when I said that as soon as we defined a structure, we looked at the linear maps preserving that structure, why we have not done that with inner products. Well, what this theorem tells you is that if you ask that your map preserve lengths, then it automatically preserves inner products if that length comes from inner products. And conversely, if your map preserves inner products, then it conserves lengths. Okay, so one direction is obvious, right? If we have a map that preserves inner products, then the norm of T of V is equal to square root of the inner product of T of V with itself. And because the inner product is preserved, that's the same as the square root of the inner product of v with v. And that is the norm of v to be for all v and v. So T is an isometry. Well, actually here, let me just say, so T preserves lengths. Since T is an isomorphism, it is actually an isometry. Right. So this immediate computation tells us that if you preserve the inner product, you preserve the length. And then since we are assuming that T is an isomorphism, that means that we actually have an isometry. Okay, so the more interesting direction is going the other way. Say you have a map that preserves lengths, you want to say that it preserves inner products. Okay, well, as we talked about last time, if you have a length that comes from an inner product, then you can recover the inner product from the length. So this is different cosmetically if you're working with the real numbers or the complex numbers. So let's say that we're working with the real numbers. So one formula for the inner product in terms of the length is that the inner product of v1 with v2 is equal to 1/4 of the inner product of v1 plus v2, sorry, of the length of v1 plus v2 squared minus the length of v1 minus v2 squared. Okay. Well, if you have this formula, then checking the T preserves inner products is easy, right? Because you just start with the inner product of T of v1 with T of v2. You apply this formula to say, well, that's 1/4 of the length of T of v1 plus T of v2 squared minus the length of T of v1 minus T of v2 squared. Then because T is a linear map, I can write this as T of v1 plus v2 squared minus the length of T of v1 minus v2 squared. And then because T preserves lengths, I can write that as the norm of v1 plus v2 squared minus the length of v1 minus v2 squared. And then because v satisfies this equality, this is equal to the inner product of v1 v2, as we wanted to check. If you're working with the complex numbers, then there's also a formula for the inner product in terms of the norm. It's slightly longer, but here we go. The inner product of v1 with v2 is equal to 1/4. Take norm of v1 plus v2 squared minus the norm of v1 minus v2 squared plus I times norm of v1 plus iv2 squared minus I times norm of v1 minus iv2 squared. Okay, and that will recover the inner product from the length. And so a similar computation shows that the inner product of T of V1 with T of V2 is equal to the inner product of V1 with V2 for all V1, V2 in the vector space, and so we're done. Okay, I've noticed that I say length a lot more than I say norm. So just know that those are synonyms. I'm using them equivalently. Okay, a convenient alternate way of writing this so instead of saying that T of V1, T of V2 inner product is equal to the inner product of V1 with V2 for every V1, V2, in V, we could say that T of V inner product with W is equal to the inner product of V with T inverse of W for every V in V, W in W. Okay, so notice that I'm using T inverse, but that's okay because T is an isometry, so T is an isomorphism in particular. Let's check that these are equivalent. Right, so we have to check both directions. So the first direction, assuming that T preserves inner products, we have the inner product of T of V with W. Well, we could write this as T of V and then T of T inverse of W. And then because T preserves inner products, that's the inner product of V with T inverse of W. That's what we wanted. And similarly for the opposite direction, if we assume that T of V inner product with W is equal to V inner product with T inverse of W, then we have, so let's say you have T of V1, T of V2, and you're taking the inner product. Well, T of V2 is a W, right? So this is the same by assumption as V1, T inverse of T of V2. And that's V1, V2. Right, so that shows this equivalence. So it can be useful to think of a isometry between inner product spaces as a isomorphism satisfying this identity. So for example, consider R theta mapped from R2 to R2. So remember, this is just counterclockwise rotation by angle theta. This preserves inner products, and so it satisfies the corresponding identity, which here would look like this. The inner product of V rotated by theta with W is the same as the inner product of V with W rotated by minus theta. Right, so one way of reading this is that the angle between the two vectors we get by rotating V counterclockwise . by theta and comparing with W is the same as the angle between the vector V and the result of rotating W by theta clockwise. Right. So if we just think about the inner product with real vector spaces as giving us some notion of angle, which is true if you have unit vectors or vectors of the same length, then that gives a very intuitive interpretation of this equality, right? It just says this, that if you rotate one way and check the angle, it's the same as if you rotate the other vector the other direction by the same amount and then check the angle. Okay. Great. So next, continuing another theme, we can understand any property of a linear map by seeing what it does to a basis. Right. So for example, we saw that a linear map between two vector spaces is an isomorphism if it takes a basis to a basis, right? And it's if and only if it takes a basis to a basis. So now let's let V and W be finite dimensional inner product spaces. And let T be a linear map between V and W. Okay, then the following are equivalent. Okay, first statement, there is an orthonormal basis V1 through Vn of V such that its image under T, so T of V1 through T of Vn, is an orthonormal basis of W. Right, so this is completely analogous. For an isomorphism, we wanted that the image of a basis under T is a basis. Here we want that the image of an orthonormal basis is an orthonormal basis, and we are going to claim that that is equivalent to T being an isometry. And in turn, that's equivalent to whenever V1 through Vn is an orthonormal basis of V, then T of V1 through T of Vn is an orthonormal basis of W. Okay, so the claim is that if you do this for one basis, then you do it for all bases. Okay, so let's prove this. So we want to show that these statements are equivalent. So we're going to show that A implies B, which implies C, which implies A. So then if any one of these statements holds, they all hold. Okay, so A implies B. So we get to suppose V1 through Vn is an orthonormal basis of V, and T of V1 through T of Vn is an orthonormal basis of W. We want to show that T is an isometry. Right. So we're assuming A, we want to prove B. Okay, we want to show that T is an isometry. So we want to show that T preserves norms. Right, so given, well, actually, we want to show that T is an isomorphism that preserves norms. So let's start by showing that T is an isomorphism. So first, T is an isomorphism since it takes a basis of V to a basis of W. Okay, perfect. So we know it's an isomorphism. So now we just want to check that it preserves lengths. So given a vector in V, we want to show that the size of T of U is equal to the size of U. Okay, if we do this for an arbitrary vector in V, we're done. Okay, great. So let's start the size of T of U. Okay, well, this is equal to the size of T. I'm going to write it in terms of this basis, right? So this will just be the inner product of U with Vj times Vj. Right, so because it's an orthonormal basis, I know the coefficients that give U as a linear combination of the Vj's. Next, I'm going to use that T is a linear map to write this as the size of the sum, j goes from 1 to n. I'm going to pull out the coefficients, these u vj's, and then I'm just going to have t of vj. Taking the norm. Okay, so let's go ahead and square this just to make things less messy, so I don't have to put in some square roots, because next what I want to use is the Pythagorean theorem, right? So I know that the image of this orthonormal basis under T is an orthonormal basis, so I know that each of these terms is orthogonal to each of the other ones. So then by the Pythagorean theorem, I can write this as the sum, j goes from 1 to n, of the norm of u vj inner product times t of vj, norm squared. Okay, and then I can pull out the coefficients with their modulus. And then I'm left with t of vj squared. And the norm of t of vj squared is equal to 1. So I can write this as sum j goes from 1 to n of the modulus of the inner product of u with vj squared. And then I'll just say similarly, if I start with the norm of u squared, then I can proceed in the same way, write this in terms of the orthonormal basis, so u of vj inner product times vj, and then because it's squared, and then because each of these terms is orthogonal to each of the other ones, I can use the Pythagorean theorem to write this as norm of u of vj times vj squared, and then I can pull out the coefficient, sum j goes from 1 to n, modulus of u of vj squared times the norm of vj squared, and then because this is an orthonormal basis, the norm of vj squared is equal to 1, and so we're just left with the sum of the inner product's modulus of the inner product of u with vj squared. So we got the same answer here as here, and so the norm of u is equal to the norm of t of u, as required. So let me point out that this is a computation we had already done. We have already seen that if you use an orthonormal basis, then the inner product, sorry, the length of a vector u is equal to the standard length, or the length with respect to the standard inner product of the corresponding column vector in Cn, or Rn, Fn, whichever F you're using. All right, so we could have also just recognized here that we had gotten the norm of u squared, but I thought might as well just do the computation again because it's not very long. Okay, so that proves that A implies B. Next, we want to show that B implies C, right? So we get to suppose that T is an isometry. We want to show that whenever V1 through Vn is an orthonormal basis of V, T of V1 through T of Vn is an orthonormal basis of W. Okay, so suppose we're given V1 through Vn, which is an orthonormal basis of V. Okay, well, we know that T is an isometry. So T isometry implies T is an isometry, implies T is an isomorphism, implies that T of V1 through T of Vn is a basis of W. Okay, so great. We know it's a basis, so we just need to check that these are orthonormal. So let's say, moreover, the inner product of T of Vj with T of Vk, so because T is an isometry, that is equal to the inner product of Vj with Vk, and that's either equal to 0 if j is not equal to k, or 1 if j is equal to k. So this basis, T of V1 through T of Vn, is an orthonormal basis. Excellent, so that's what we wanted to show. And then finally, C implies A is trivial, right? Because if every time you have an orthonormal basis of V, its image is an orthonormal basis of W, then A, which just says that there is an orthonormal basis of V whose image is an orthonormal basis of W, is just saying that there is an orthonormal basis of V, and we know that that's true by Gram-Schmidt. So there's nothing to prove for C implies A, and that finishes the proof that this is an equivalence. Okay, wonderful. So an immediate corollary, if V and W are finite dimensional inner product spaces, then V is isometric to W if and only if the dimension of V is equal to the dimension of W. Okay, so if you want to distinguish between different inner product spaces, and you only care about the inner product structure, so you only care about the vector space up to isometry, then there's only one invariant, the dimension. Let's go ahead and prove this. One direction is trivial, right? If you have isometric vector spaces, then in particular, they are isomorphic, and so they have the same dimension. On the other hand, let's say that you have two inner product vector spaces of the same finite dimension. If we get to assume this, we want to show that they are isometric. Okay, so here we go. Pick an orthonormal basis of V, call it V1 through Vn, and pick an orthonormal basis of W, call that W1 through Wn, right? And I'm using that they have the same dimension to say that there are n elements in each of these, right? We know that there exists, right, exactly one linear map T from V to W such that T of Vj is equal to Wj for all j. Right, so we know if you give me a basis of V with n elements, then you can pick any n vectors in W, and there is one and only one linear map that takes the jth element of that basis to the jth vector in W. Right? Now, by the theorem, T is an isometry. Since it takes an orthonormal basis of V to an orthonormal basis of W. Okay, wonderful. So if you're only looking at finite dimensional inner product spaces, then up to isometry, there's only one per dimension, right? So just like there's only one vector space over a given field with a given dimension up to isomorphism, there's only one inner product space as well, right? So if you're working over the complex numbers, then in dimension n, the only vector space up to isomorphism is Cn, and the only inner product space up to isometry is Cn with the standard inner product, right? This is not true if you're looking at length spaces, normed spaces. For example, on C2, you could consider the little L1 norm, or you could consider the standard norm, and those are not isometric, because if they were isometric, then the little L1 norm would be given by an inner product, would come from an inner product, and we know that it does not. Okay, here's a simple corollary about the matrix associated to an isometry. So let's say that BV and BW are orthonormal bases of V and W respectively. A map T linear between V and W is an isometry if and only if the columns of the matrix associated to T with respect to these spaces form an orthonormal basis of Fn. Okay, so key thing is that these are orthonormal bases. Okay, this is very much not true if you're working with bases that are not orthonormal, right? And that makes sense, right? The matrix associated to a linear map is only going to be able to notice things about how the map behaves with the inner product if the bases were chosen to reflect how the map behaves, how the vector spaces behave with respect to their inner products. Okay, so let's prove this. Well, let's say that the basis for V is the vectors V1 through Vn. Then the columns of this matrix are, well, take T of V1 and then express that in the basis for W. Take T of V2 and then express that in the basis for W, and so on until you take T of Vn and express that in the basis for W. Okay, now T is the linear map between V and W, is an isometry if and only if the list T of V1 through T of Vn is an orthonormal basis of W, and then that's equivalent to having the list we were just interested in, T of V1 expressed in the basis BW up to T of Vn expressed in the basis BW is an orthonormal basis of Fn, right? And this is because we've seen that expressing a vector with respect to an orthonormal basis, the coordinates associated to an orthonormal basis, gives you the takes the inner product to the standard inner product. So when I take this orthonormal basis and I express it in terms of an orthonormal basis of W, then what I get is an orthonormal basis with respect to the standard product, inner product on Fn. And that's what we wanted to show. Okay, very good. We'll stop there and pick it up from there next time.